you don't want to end up with no freshmen. You don't want to end up with no sophomores, or you don't want to end up with an all-male sample or all-female sample. So in order to ensure that every group is represented, you pick a random sample from each group. You said all that. Okay, so what is disproportionate allocation? Give me an example of disproportionate allocation. What does it mean to be disproportionate? Yeah. Two groups of equal numbers like this, 50 males, 50 females. Okay, and what about them? How so? Male has a lower probability of getting a what? A reward? No, disproportionate means that I take a sample of a different size even though the numbers in the population are the same. Meaning in the population I have 50 males and 50 females, but when I choose a sample, I choose 4 from here and 8 from here. Not in proportion with the original ratio from the population itself. Get it? Why would I do that? Yeah. Yeah. To account for extra variability in one group, you take a larger percentage from that group. Okay. Can we look at the problem on page 3? And can we do this problem? Can you do this problem and then we'll go over it? A sociologist wants to learn about the opinions of employed adult women on government funding for daycare. He has a list of 520 employed women. 520 employed women, 20% of whom are members of local business, 20% local, and 80% of whom are members of a professional club. He decides to randomly select 25, let me write here sample, 25 women of the local business and 75 women of the professional club to form a sample of 100. Employed women. What type of sampling? Obviously it's stratified, but what they're asking is proportionate or disproportionate allocation. What do you think? In the original population, local to professional is 1:4 ratio, correct? And this is a 1:3 ratio. So it has to be disproportionate. So A, stratified random sampling, disproportionate allocation, because 2 to 8 is 1:4, and that's not equal to 25 to 75, which is 1:3. Follow me? Part B. Do you follow me? Part B. Suppose that 15 of the 25 are in favor. So let's write here in favor, 15 out of the 25, and 60 out of the 75, for a total of 80, for a total of 75. And give the overall estimate of the proportion of employed women that favor government funding for daycare. So I have to do the in favor rate here. Shall I wait for you to do it, or should I just do this problem? Go do it, would you? I want the overall estimate of the proportion in favor of government funding. It's exactly the same problem that I did with the freshman, junior, sophomore, senior last time. I did do that in this class, right? No? Yeah? Okay. It's a weighted average, right? So simply take the numbers in favor, 15, out of 25, and apply that to the percent of the population that's local. So 20% of my population is local. I don't care that 20% of 520 is 104. I don't care about that. Because they... see, in the previous problem with the freshmen and the sophomores, they gave me the raw data, like 50 freshmen out of 350. So I was able to say 50 divided by 350 is 1/7 of the population. But here I already know that this is 20%, so 1/5 of the population. So I don't have to do that. I don't have to find the number and then divide again just to get 20%, because I would be wasting my time. So this is just 20% of the population, and this is the in favor rate, plus 60 over 75 from here, and that applies to 80% of the population. Follow me? Yes or no? So what do you get? So this looks like it's 3 out of 5, which is 0.6, times 0.2, plus 15 4s are 60, and 15 5s are 75, so 0.8 times 0.8. So 0.12 plus 0.64 gives me 0.76. That's my final answer. Have I managed to confuse anybody? Do you have a question? Let's go to the next page. So this would be on page 4 of your class notes. Let's talk about 1 in K systematic sampling. Let me make this a little smaller so you can see. It's the next sampling method. Let's say that I want to do 1 in 5 systematic sampling. Basically, that means you're going to choose every 5th member, 1 in 5. So let's say that I'm starting with a population of 28 people. First thing I want to do is label the population. So everybody gets a label, 1 through 28. And then the process is, if you're doing 1 in 5 systematic, you look at the first 5 members and choose one randomly. Let's say that I choose person number 4. I can choose anybody randomly from amongst these 5. Let's say that the first member is person number 4. From there, I choose every 5th person because I'm doing 1 in 5 systematic. So 4 plus 5 is 9 because my K is 5. 9 plus 5 is 14. 14 plus 5 is 19. 19 plus 5 is 24, and then I stop because the next one would have been 29 and there are only 28 members. So this sample has 5 people in it. Person 4, 9, 14, 19, and 24. Had I started with person number 1, I would have had 1 plus 5 is 6, plus 5 is 11, plus 5 is 16, plus 5, plus 5. I stop at 26. Because the next one would have been 26 plus 5, which is 31, and I don't have 31 members. So this time the sample has 6 members in it. Because I started early enough at person 1 that I was able to squeeze in one more member before I hit the 28th person. Follow me? So when n, my n is 28, when n is a multiple of k, my k is 5, that is when all samples will be of size n over k. So had my n been 25, suppose my capital N was 25. If I was doing 1 in 5 systematic sampling, all the samples would have been of size 25 divided by 5, which would have been 5. But since this n of 28 is not a multiple of k equals 5, some will be bigger and some will be smaller. Do you see what I'm saying? So let's say I was doing 1 in 4 systematic sampling and I had 28 members. 1 in 4 systematic, so K is 4 and N is 28. All the samples will be of size 7 because 28 divided by 4 is 7. But here N is 28 and my K is 5, which is not a factor of 28. Therefore, some are bigger, like this. This has 6 members and this has 5 members. Makes sense, right? Yes or no? So the next question is, what is the probability that person number 26 will be in your sample? Let's say that's the question. What's the probability that person 26 is in your sample? What do you think? Let's say these are the choices. These are your choices. Probability of number 26 in sample. And the choices are the following. A, 1, B, 0, C, 1 out of 6, D, 1 out of 28, and E, 1 out of 5. And I'm doing 1 in 5 systematic sampling. And I want to know what is the probability that person number 26 is in the sample. What do you think? What do you think? Between C and E. I agree. It's E. Yeah. Why is it E? And that's how you'll reach 26? You start with 1, you reach 26. That's okay, so 1, who cares, right? So if you start with 1, you reach 26. I agree with you. Therefore, where do you get the 1 out of 5 is my question. No good? It's not 1 out of 5? You were saying 2. You were saying start with 2, you end up with 26, right? But it's not 2, it's 1. So who cares? It's okay. So it's 1. So how do I get 1 out of 5 out of that? That's my question. Yeah.
So I would say it depends on the first when you start, and since there's only 5 options for the beginning, then there's 1 chance out of 5 that you're supposed to.
Do you all hear her? Yes. You don't hear her? Is there anyone who didn't hear the answer? Okay, one more time.
So since when you start off, there's only 5 options, and only one of them will give you 26, the probability that you're going to end up with is 1 out of 5.
I agree. So she's saying that you can only end up with 26 being in the sample if you start with person number 1. Do you agree with that? And the beginning of the process is you have to pick one of them randomly, right? So 26 is in the sample when you start with 1. What is the probability of starting with 1? 1 out of 5, because the process, the way you do this is 1 out of k members initially are picked, right? So the probability of picking person 1 is 1 out of k, which is 1 out of 5. Finished. So this is the answer. And that is true for no matter what number I pick here. If I say, what's the probability that 27 is in the sample? You would say, it's the probability of starting with person number 2. What's the probability of starting with person number 2? 1 out of 5. So 1 out of k is always the answer to this question, no matter who we're talking about. Makes sense, right? Do you have a question? Okay, so the problem that's provided in most of the textbooks is this Delta Airlines example, where the configuration of the aircraft looked like this, with the 2 aisles, 3 seats in the middle, and 2 seats by the window and 2 seats by the other window. And they made a statement that said, in 1 out of 7 systematic sampling, every person polled rated the flight 10 out of 10. Do you see anything wrong with this? In 1 of 7 systematic sampling, every person polled rated the flight 10 out of 10. Is there any issue with this? And they started with this person right here. And they're doing 1 in 7 systematic sampling. Yeah. Right there on the screen, what happened? It's biased. Why is it biased? How? How so? Why is it biased? What do you mean you don't know who you're picking? I don't understand that. No, you're not picking 7 random people. You're doing 1 in 7 systematic sampling. So 1, 2, 3, 4, 5, 6, 7. And they picked this guy. They picked person number 5. So why is that biased? What do you think? Yes, location. What about the location? 1 second. What about the location? He's not. He's sitting at the aisle. You're so close that I just want you to say what I want you to say. So could you keep talking? He's not sitting in the middle. He's at the aisle. He's in the front row on the aisle. So why is that biased? What's wrong with that? First class? Okay, first class. First class would never have 3 seats like that, but anyway. Anyone else? Yeah? Notice, yes. Notice that they're doing 1 in 7 systematic and there are 7 across, right? Which will guarantee that everybody that they poll is on the aisle, right behind one another, right? Which means that this guy who cannot get out and the guy behind him who cannot get out because the person next to them is asleep for 7 hours on a flight to Milan or whatever, is never going to get polled. That's why it's biased, because bias means that everybody doesn't have the same chance of being in the sample, right? So the minute they determine that they're going to do 1 in 7 systematic sampling, and the minute that they pick the first guy on the aisle, that means everybody's going to be on the aisle because there are 7 people across, right? So how fair is that? Polling these guys and polling the guys by the window is a different story. Agreed? So that's why it's biased. So systematic sampling is biased in general because once you pick the first member, the next member never has a chance of being in the sample. And the guy before him has no chance of being in the sample either. Unless you pick every single person, in which case it's not going to be a sample, it's going to be a census. Follow me? Yes or no? Okay. So systematic sampling is always biased, and systematic sampling, the probability of picking any one member is always 1 out of k. That's what will get tested on the test, on the exam. Okay? Next method, next page. So next page is still talking about the same thing. Let's go to page 6. Page 6 is talking about a new method, which is called cluster sampling. So far we've talked about simple random sampling, stratified random sampling, 1 in k systematic sampling, and now this one, which is cluster sampling. Cluster sampling is the process where you take your population and you divide it into clusters, which are mini versions of the population itself. For example, classrooms are clusters. A cluster is a mini version of the entire population. So let's say that I want to determine how many hours you guys exercise. The students at Stony Brook University, how many hours a week do you exercise? I claim that if I take the whole population of the student population at Stony Brook, and I look at classrooms, I claim that within the classroom, I will see all kinds of people. People who don't exercise at all, and people who exercise every single day. How many of you exercise every day? Can you raise your hand? 1, 2, 3. 3 people exercise every single day. How many of you exercise 3 times a week? Okay, so maybe another 6 or 7 or 8 people. And how many of you don't exercise at all? Raise your hand up high so everyone can see. How many? How many? Lots, like 20. Okay? So do you see that within one cluster, I got all the variability that I needed? I got the people that don't exercise, and I got the people who exercise like fiends every single day. Right? Showing me that all I have to do is look at a few of these clusters, because all the variability in the population will be captured within each cluster. You follow me? So the way this process works is that you randomly choose just a handful of clusters. So maybe you would look at classrooms that are in session at 7 p.m., like your class, and maybe you guys, what is this, AMS 110? Yeah? So AMS 110 is one of the clusters, and then psychology, whatever, however those numbers work, is another cluster, and let's say music is another cluster, and art is another cluster. Within each of these clusters, I will find the no exercisers and the people who exercise every single day, and every variation in between. So your sample will consist of the 70 people in here, and the 90 people in music, and the 40 people in psychology, and the art class of 100 people. My total sample will be 90 plus 100 plus 40 plus 70 plus 20, let's say. That's the total sample. And it will contain all kinds of people, guaranteed, because every cluster contains all kinds of people. Get it? How will this be biased? Is there any bias here, do you think? Yeah. Wait, music class or art? Which, this is music, this is art. Art. What, artists don't exercise?
Oh, no, I'm not talking about, like, there might be like a bias in, like let's say artists don't exercise that much.
Oh, yeah?
Let's say,
Oh, and AMS people exercise? Is that the implication? Yeah, kind of. You can stretch it and say, what if it's a gym class? Right? Or what if it's a weightlifting class and everybody exercises every day? In that case, you would get biased results because your cluster is not a version of the mini population. It's not a mini version of the population. That's kind of what you're getting at, right? That maybe these people, maybe these guys don't exercise as much as everybody else in the student body. It's true. If one of those clusters happens to be a gym class, then maybe those guys are a little more exercise-oriented than the math people or the psychology people. It's true. In that case, you would have bias. Yeah. There could be more variability in one. Yeah, but you have no way to know because you're going to pick these out of random number table, right? So you're going to label every cluster, and then you're going to label them, maybe multiple labeling, and then you're going to pick them randomly. So you won't know what the variability is, and you shouldn't know, right? Otherwise, it's going to impact your results. Okay. So the thing that will get tested on this on the exam is that differences, D stands for differences, within are large. Differences within the cluster are large, meaning assuming that the variability is large within the cluster. Very different from stratified, because in stratified, the differences between the strata was large. But within the group, the differences were small. This is just the opposite. This is differences within each cluster is large, but differences between clusters is small, because you are expecting that the clusters are similar to one another as a whole, but within the cluster you see all kinds of people. Get it? Do you have a question? So it says that here on your page 6. Let's go to page 7. Page 7 is multi-stage sampling. This is just any combination of the methods that you learned so far. So maybe first do systematic sampling and pick up every 100th member, and then follow it by stratified random sampling. Something like that would be called multi-stage sampling. And then there's something called convenience sampling. Convenience sampling is extremely biased. Convenience sampling would be like me standing outside Penn Station and saying, what did you eat for breakfast? What did you eat for breakfast? What did you eat for breakfast? It's garbage results, but it's results nonetheless. But they're totally biased because people who don't walk past Penn Station would never have a chance of getting polled. Right? So that's convenience sampling. You get some results, but what you get is rubbish. Okay. What is a confounder? Do you know? Anybody know what a confounder is? Anybody want to take a guess at what a confounder is? Let's say you have two variables. Inactivity is an independent variable, and heart disease is the dependent variable. And let's say you have, yeah? Two things that happen at the same time, but have anything to do with one another? Yeah, kind of. So let's say that you are trying to study the relationship between inactivity and heart disease. So you might think that inactivity, which is the explanatory variable, the independent variable, leads to heart disease. Perhaps, maybe. I'm trying to study this relationship. But I better control for other factors like perhaps age. See, as people age, they tend to be more inactive, and as people age, they tend to develop more heart disease. So maybe I need to control for this other factor, age, that influences both X as well as Y. Here, this is X, this is Y. Age would be a confounder in this case. Get it? Yes or no? So if you ignore age, you might falsely conclude that inactivity causes heart disease. You have to look at and control for confounders when you're looking at relationships between X and Y. Follow? Okay. So that's one. Confounding is a very complex topic. So this is the simplest example that I could think of to tell you. Okay, there's something also, here's another example here. Estrogen therapy causes breast cancer. Perhaps. Maybe this is the independent variable and this is the dependent variable. It's a possibility that estrogen therapy causes breast cancer. But maybe it's not the estrogen therapy that's causing the breast cancer. Maybe there's a family history of breast cancer to begin with that's causing the breast cancer. In this case, this is a different kind of confounder. This is the picture for this relationship would be, is X causing Y or is Z causing Y? That's slightly different than this one. This one is X causing Y or is Z causing X and Z causing Y? You see the difference? This is also confounding. This is also confounding. Here's another example. Sulfur dioxide, a relationship between sulfur dioxide and chronic cough. Is the sulfur dioxide causing the chronic cough, or is the person that I'm looking at a smoker and that's causing the chronic cough? So this is this one. Is X causing Y or is Z causing Y? That's also a confounding relationship. So sometimes they talk about confounders just affecting Y, and sometimes they talk about confounders impacting X as well as Y, like our age and heart disease, age being the confounder and inactivity and heart disease example. All these examples are examples of confounding. Let's look at the next page. Page 1 in the next set of notes. Look at this one. This is some ridiculous relationship here. As ice cream consumption goes up, homicides are noted to go up also. It's ridiculous, right? This is called a spurious relationship. So what turns out here is that as temperature goes up, ice cream consumption goes up. And as temperature goes up, homicides go up because more people are out and about, so there's more crime. So this variable is impacting both X as well as Y. And this relationship between ice cream and homicide is called a spurious relationship. Follow? Correlation exists between ice cream consumption and homicides, but there is no causation. So correlation does not imply causation. Have you heard that before? This is a prime example of that. Ice cream consumption doesn't cause homicides to go up. There's some other variable like temperature that's causing both of them to go up. Any question? How many of you are bio majors? So you have to have seen confounders before, right? Can you give me a better example of confounding than I've given you? I've talked about estrogen, I've talked about inactivity, I've talked about ice cream and homicides. Can you give me a better example of confounding than I've given you? Now that you know what a confounder is? Nobody? Nobody? Duran, what about you? You're a bio major, Duran. I can't hear you at all. Sorry. You eat too much sugar. Can I write this? Okay, sugar consumption goes up. Insulin. Okay. Okay. And then, is there a confounder? So this is, if you eat more sugar, your body produces more insulin. And then, is there a confounder in there? So the more insulin that's produced, it lowers your blood sugar. And where's the confounder? Like this, blood sugar. So where's the is there a confounder in this relationship? Meaning something that affects this or both of them? I don't know any bio, but I'm willing to listen. Yeah. Fruit consumption? Is that the same as sugar consumption? Natural sugars cause insulin spikes or not, right? They say that natural sugar, like fructose, doesn't cause insulin spikes or doesn't hurt you. So would that be a confounder? Would it impact this and this? I don't know if it's a real confounder. Mm-hmm. So you're saying there's two types of sugars, and one type of sugar doesn't cause an insulin spike. I don't know if that would be considered a confounder. Yeah. Go ahead.
And the confounder be the insulin and like an increase in diabetes be the other one?
So what's the independent variable? Make something up. You can make it up.
I was just going to say that sugar and diabetes.
So the more sugar you eat, the more chance of diabetes? Is it true? I don't think that's true. Right? Just because you consume sugar doesn't mean that you become a diabetic. Right? I could be wrong. I know no bio, but I think some people eat as much sugar as they want and are never diabetics. I think you're a diabetic if your body is not able to handle that sugar. Is that correct? I beg your pardon? It does? So is it guaranteed that someone who eats no sugar will never be a diabetic?
No, it's not necessarily in every person, but there's,
Okay.
because you get a metabolic disorder where your body becomes desensitized.
Okay, so sugar goes up, the chance of diabetes goes up? Is that true? Okay, and then where's the confounder? So what about insulin? What about, I have to be clear. So what about the insulin? So insulin, what about the insulin? Is it affecting only the diabetes, or is it affecting both, or what? I have to be clear. Help me. So what? If you take more insulin, you will consume more sugar? Go ahead, sir. Type 1 diabetics will not produce their own insulin? Okay, so would insulin be a confounder? No, right? Yeah.
You say like high fructose corn usage in products, and then obesity going up, and confounding is just people eating at high calorie. They're calories.
Okay, so let me put this up and see what happens. So, I'm sorry, go again. What's the independent variable?
High fructose corn syrup usage in products.
Okay, high fructose corn syrup, okay.
Usage goes up, and obesity goes up.
Uh-huh.
But it can also be due to a high caloric food intake and going up.
That's a confounder. So, more calories could be making you fat. So this would be a confounder. This would be a confounder. I agree with you. The insulin stuff I still don't get, really. I didn't see that as a confounder. I don't see it. So you can talk to me after class and convince me. They don't. So this would be the same as estrogen therapy, breast cancer, familial aggregation. Yeah, so more calories would not be affecting the high fructose, right? Okay, anything else? Any other examples that everybody can understand? Yeah. Okay. Increase anxiety. As anxiety increases, what happens? Increase in depression. Okay. Is it true? Okay. Increase in stress. Okay. So as your stress goes up, your anxiety levels go up, and as your stress goes up, your depression goes up too. Is it true? Okay. High fat. Coronary artery disease and smoking. Okay, so are you saying that people who smoke eat higher fat foods? Yeah, just this one, right? It's always just X, Y, and Z impacts Y, right? But smokers are not associated with high-fat diets, are they? Or do you see someone who's smoking is eating French fries too? I don't know. There could be a relationship between smoking and high fat, right? What about smoking, drinking, and bad stuff happening? Like this. Smoking goes up, death goes up. Or whatever, cancer goes up, right? Let's call it cancer. And how about drinking? So drinking goes up, cancer goes up, drinking goes up, smoking goes up. That's a yes. The higher probability of drinking is associated with the higher probability of smoking. That is true. So now this would be this one impacting this and this. That's also a confounder. Yeah, liver cancer, for sure. Right? All the drunks have cancer of the liver. I'm not sure, but their death goes up if you're a drinker. I mean excess drinking, not the ice wine once a month. Yes? So there are two examples of confounding. One example of confounding is like this. X impacts Y, Z impacts Y, therefore Z is a confounder, right? That's loosely a definition of confounding. But a better example of confounding is X impacts Y perhaps, and Z impacts X, and Z impacts Y, and therefore Z should be controlled because Z is a confounder. So if you look up confounding, you will see examples of both of these kinds of diagrams. Yes. I beg your pardon? Okay, let's go. Okay, CO2 goes up. That's going to be the confounder, okay. No, one can go up, one can go down. Which one? Coral reef. Coral reef density goes down. Okay, so is temperature the independent variable? So is temperature going up making this thing go down? Okay, so temperature is the X variable going up, makes coral reef density go down. Is it true? Perhaps. And then CO2 levels are the confounder. Does CO2 make temperature go up? I don't know. Yes? Why? How? Okay. Okay, so then this would be a confounder. Yes, perhaps. You're right. So we were here. Difference between observational studies and experiments. The major difference between observational studies and experiments is that in an experiment, you are manipulating the independent variable and observing effects on the dependent variable. Whereas in an observational study, you are not manipulating anything. So one example of an observational study would be a case report or a case series. For example, when you go to the doctor and they take a history, that's a case report. If they're doing it on many people, it's called a case series. That's the first type of observational study. No manipulation was done on the subject. They weren't given a sugar pill, some weren't given the drug. So there's no manipulation of any kind. You're just observing and taking a report. The next one is a case control study. Cases are people who have a certain condition, and controls are people who don't have that condition. It's a retrospective study, meaning that data is collected from the past to see if certain factors cause the disease. For example, Can you give me an example of a case control study? Yes? Asthma, perhaps, right? Exposure to asbestos causing asthma. That would be a case control study. You would be asking asthmatics and non-asthmatics if they were exposed to asbestos. If the asthmatics have had a larger exposure to asbestos. That would be a case control study. It's retrospective, going back in time. How about a longitudinal study? What would that be? A cohort study would be a longitudinal study. How about following people who use cell phones and people who don't use cell phones to see if the people who use cell phones have a higher incidence of brain damage? Or how about following smokers and non-smokers to see if smokers have a higher incidence of whatever you're studying? How about following people who are vegans and following people who have normal diets to see if the vegans develop some kind of risk to some disease or not? That would be a longitudinal study. In other words, you are following people over time to see if they develop a certain condition. The people are made up of, there are two sorts of people you are following. People who use a certain something like smoking and people who don't. So you would decide at this point in time to follow people for a period of 3 years to see, for example, if Xanax causes Alzheimer's. You might follow Xanax users for 15 years and non-Xanax users for 15 years to see if the Xanax users have a higher rate of Alzheimer's. That would be a longitudinal study. Follow me? Okay, then there's cross-sectional studies. Cross-sectional study takes a snapshot at this moment in time. For example, measuring the cholesterol levels of runners and non-runners. That's a cross-sectional study, meaning you are not looking back, you're not following people over a period of time. You're just looking to see right now if the cholesterol levels of runners is lower than the cholesterol level of non-runners. That would be a cross-sectional study. But it's an observational study because you're not manipulating anybody or giving one a drug and giving the other a placebo. That's not occurring. On the other hand, an experiment is when certain subjects are given the treatment and others are given a placebo, and then you look to see whether there's a difference. For example, the polio vaccine trial. The vaccine was given to 200,000 odd people, and the placebo was given to 201,000 odd people. And it was observed that 33 of the vaccinated people developed polio, whereas 115 of those given the placebo developed polio. This is an experiment because some were given a vaccine and some were not. This is a completely randomized design, meaning that the people who were given the polio vaccine were picked randomly. So this polio vaccine experiment was a completely randomized design. It doesn't have to be completely randomized. You can have an experiment where the people who are given the treatment and the placebo come in as pairs. That would be called a matched pair design, where the subjects enter as pairs, and one of the pair is chosen to receive the treatment and the other one by default receives the placebo. that would be called a matched pair design, and we talk about matched pairs a lot in this class. Then there's the randomized block design, where it is known that male and female hearts respond differently to the same medication. So you are not able to give a group of people placebo and a group of people, the same group of people, which is mixed, male and female, one part of that group gets the placebo and one part of that group gets a heart medication. You cannot do that because male and female hearts respond differently to heart medication. So you first have to separate the group into male and female, which is called blocking by sex, and then you run that experiment on the male hearts and on female hearts separately, because they're going to respond differently to begin with. So you would first separate the group into males and females, and then you would give some of the females placebo and the rest of the females the drug, and you would do the same thing on the male side and separately observe male hearts and female hearts, because it is known ahead of time that they would respond differently anyway. So you would be blocking by sex in this case. Follow? So those are the main things you would be tested on an exam. You would have to know that an experiment is one where the subjects are manipulated. An observational study is one where nobody's manipulated. If you're following people over a length of time, it's a longitudinal study. If you're looking back in time, it's a retrospective study or a case-control study. If you're looking only at this moment in time, it's a cross-sectional study. That's all. What's the placebo effect? Do you know? Yeah. So if you gave me a sugar pill and my headache went away because I thought I was taking Advil, that would be the placebo effect. What's the nocebo effect? Do you know? Yeah. Yeah, so a nocebo effect is when you realize that you haven't taken your medication, you all of a sudden start having palpitations. But you wouldn't have had them had you not realized that you didn't take your medication. That's the nocebo effect. Okay, let's see what else we have to mention in conjunction with experiments. Matched pairs we did, cohort we did. I think we're done with that. I think we're done with experiments versus observational studies. We can move on. Let's go to the next page, page 3. Every variable that you observe in an experiment or a study, an observational study, is either going to be categorical or quantitative. A categorical variable, for example, sex of patient or gender of patient. What's the difference between sex and gender? Do you know? Yeah. Exactly. So sex is how you are born, biologically speaking, and gender is how you view yourself. Those are both qualitative random variables. Age of the patient is quantitative random variables. Salary of a worker would be quantitative. The handedness of somebody would be qualitative, whether you're right-handed or left-handed, that would be qualitative. So every variable is either qualitative or quantitative, and there are 4 scales of measurement that exist. They are nominal scale, ordinal scale, interval scale, or ratio scale. So nominal and ordinal belong to qualitative variables, categorical variables. So the most unsophisticated scale is the nominal scale. It means in name only. So names of continents, names of colleges, names of majors, names of cities. Those are all nominal scale variables. Ordinal is slightly more sophisticated than nominal, but not a whole lot, and it still belongs to categorical variables. So an ordinal variable would be a variable that can be placed in some kind of order, like an alphabetical listing would be ordinal scale. Ranking would be ordinal scale. When you rate me at the end of the semester, you would rate me as poor, fair, or excellent. That would be ordinal because clearly it's getting better and better as you go along. Sizes of rental cars, ordinal scale. Stages of cancer and degrees of burns, ordinal scale. So kind of unsophisticated because they belong to qualitative random variables. Then we move on to quantitative random variables, where you have two scales of measurement, interval scale and ratio scale. Interval scale is different from ratio scale in that ratios are not possible. For example, calendar years, the years in which Democrats won presidential elections. You cannot take a particular year and divide it by another year and get something meaningful. So that would be interval scale, not ratio scale. Similarly, clock time. You cannot say the time of your first class, 5 p.m. divided by 7 p.m. makes no sense. So if you cannot take the quotient of two of the items in your data set, then it's not ratio scale, it's interval scale. Temperature in degrees C or degrees F is interval scale because 50 degrees C is not twice as hot as 25 degrees C. Ratios are not applicable for temperature in degrees C or F. Because if you try to convert it to F, it won't be a 2-to-1 ratio. Follow me? Ratio scale, there has to be an inherent zero or start point, and ratios have to be meaningful. For example, temperature in Kelvin is ratio scale because 0 Kelvin does mean no heat, and ratios hold up in the Kelvin scale, so that's ratio scale. Mass, volume, pressure, all of those are ratio scale. Time lapses are ratio scale because there is a 0 for time lapse, and if it takes you 20 minutes to do something, it's twice as long as it taking you 10 minutes to do that same task. So a 2-to-1 ratio makes sense when you're talking about time lapse. What about age? What about age? What scale would that be? Nominal, ordinal, interval, or ratio? What do you think? The age of a fine wine, or the age of a cheese, or the age of your pet. What would that be? Nominal, ordinal, interval, or ratio? What do you think? Yeah. Interval, why? If you're 20 and your little brother is 10, are you twice as old as him? So ratios are meaningful and possible? So what do you think? Ratio scale. Age is ratio scale because age is a time lapse since birth, right? We're not in the Korean system where you're 1 when you're born, right? Do you know what I'm talking about? Forget that. You're 0 when you're born, and you're 1 a year later. And when you're 10, you're twice as old as when you were 5. So ratios are meaningful and proper. So time lapse is a ratio scale. Age is a time lapse, therefore it's ratio scale, right? Get it? Okay, next page. Bar graphs. Bar graphs can be horizontal or vertical, and it's only used for categorical data. You hear me? You cannot use it for quantitative data. Bar graphs are only used for categories. The height of the bar is the frequency or the percentage. If you take your bar graph and you rearrange the bars such that they are in descending order, it's called a Pareto chart. So in your notes somewhere, let me go there. Let's see. I'm on page 8. I'm on page 8. They gave you some data here. Number of trauma patients by day. Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. My question is, what kind of data is this? And can I put it in a bar graph? What kind of data is this? Nominal, ordinal, interval, or ratio scale? What do you think? And would a bar graph be applicable to this data? Yeah. Interval? No. Is it numerical data? That's what you have to ask yourself. Is it quantitative or is it qualitative data? Number of trauma patients by day. Would a bar graph be appropriate? Yes? Is it numbers? Is this data numbers or is this data days? It's not ratio, it's anything but ratio. It's categorical data, and the categories are Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. And the fact that you see numbers there is the height of the bar, because that's the frequency for that day. So that means the data can only be which two scales? What do you say? Can I pick on you? The first person right here, diagonal from me. Mm-hmm. It would. It would be ordinal. Why? Why does it have to be qualitative? I agree with you. You're totally right. It's ordinal because the days come in order. Tuesday comes after Monday, right? Without fail. And every one of those days comes with a frequency. So the bar graph would be appropriate for this, and the height of the bar would be the frequency for that day. So it would be ordinal data. Nominal and ordinal are the only choices for qualitative data. And it's not nominal because it can be placed in some kind of order, right? So I understand that I can make a bar graph with this. Now, if I take that bar graph that looks like this, and I change the order of the days so that the height of the first bar is the largest, and therefore the first bar is Saturday and not Sunday like it was before, then that would be a Pareto chart. A Pareto chart is a reorganized bar graph, or reorganize the categories such that the category with the highest frequency comes first, and then in descending order following from there. And Pareto, who was an Italian sociologist, said that if you target the first few categories in your Pareto chart, you will target whatever problem you are talking about. So in this case, it's talking about the number of trauma patients. So it's like saying, if we put in more ER docs on Saturday and Sunday, it will take care of the increase in trauma patients on the weekend. So it's just a reorganized bar graph. That's all it is. And that's a Pareto chart. Only used for qualitative data, where the height of the bar is the frequency provided. Get it? Yes? Yeah. Ordinal data, because the categories come in order. Yep. So you're saying, is the Pareto chart for ordinal data? Yes. What about a circle graph, otherwise known as a pie chart? I know that everybody knows what a circle graph is here, correct? But did you know that you can only use it for categorical data? And you can only use it when depicting parts of a whole. W-H-O-L-E. So if I want to talk about, look at these two examples, the percent of Asians in different majors. Can I use a circle graph? The percent of Asians in different majors. So AMS, we are 95% Asian. Chemistry, I don't know, 68% Asian. Music, 90% Asian. Can I put that in a circle graph? Yes or no? No, of course not. I've already exceeded 100%, right? How are you going to show that in a circle graph? A circle graph could only be if I'm talking about Asians being the whole and the different majors amongst Asians. That could be placed in a circle graph. But the percent of Asians in AMS being 98% and the percent of Asians in chemistry being 68% cannot be placed in a circle graph. You get that? Okay, circle graphs are only used for categorical data. That means it can only be used for nominal or ordinal data.